Okay. Can you all see my notebook or no?
Yeah.
Okay, cool. Thank you. So, okay, I'll zoom in a bit. Okay. We have been talking a lot about NumPy. I'll briefly mention a few more features of NumPy. And I think Will also briefly mentioned the topic of interpolation. I'll briefly also talk about that again in the context of spline fitting. So I'll explain what that is shortly. We saw that like NumPy arrays are very useful. Like, if you want to do mathematical computations. Oh, okay. Just chat. Okay, it's fine. Yeah. So we talked about like how NumPy arrays are very useful for like mathematical computations. One more use of these arrays is like filter data. So so first, like, as a standard thing, I'm gonna import my standard packages, import numpy's np, and import matplotlib.pyplot.splt. Here is a new command which you probably haven't seen earlier. So what this does is that this matplotlib inline. So like it's not like super important, but it just like makes your plots look better in Jupyter notebook format. So that's all it does. And then like another thing which is also new here is I sort of like set the font for like my plots here. And so this again is just like, to like make my plots look good. So it like isn't essential. It's just like, plots, like I like plots that look good. So, why not do it? So yeah, okay. So this is just, our standard like starting things like how to import packages. Then, okay, so now let's define two NumPy arrays, call it A and B. And say I want to like obtain a certain subset of this NumPy array A. Say I just want the numbers in A that are more than 4. And turns out it's actually quite simple to do it. All you have to do is just you write A, and then you do a square bracket, and then you type the condition which you want. So I want all numbers more than 4. And so all I do is do this, and then bingo, it gives me all the numbers in A that are more than 4. Now note that this only works for this only works for NumPy arrays. So you cannot do this for lists. And so this is one more reason why using NumPy arrays is better than lists. Also, it's not just like just this specific condition. You have the freedom to choose whichever condition you want. So for instance, I can say I want all the things in A that aren't equal to 4. And as you mentioned last time, if you want to show not equal to sign encoding in Python, it's just the exclamation mark and then followed by the equal to sign. And so if I run this, we get all the elements that are not equal to 4. And so you can see 4 is missing here. So that's good. Another like feature of this, which I would say is the most important feature, is that one can like filter over multiple lists. So not lists, my bad. Filter over multiple NumPy arrays. So say you have two arrays that have the same length. So it's crucial that both of these have to have the same length. If they don't, then this will not work. So here we have two arrays, A and B, and they have the same size. And say I want to filter values in A based on values in B. So I want, so like say like, that there's a one-to-one correspondence between A and B. And so if I want to choose the elements in A that in B have values less than 30, all I have to do is, again, is the same thing again, is I type A, and then in square brackets, I put the condition which I want, which is B less than 30. And if I run that, it gives me 1, 2, which makes sense because 1, 2 here, their corresponding values in B are 10, 20, which is smaller than 30. So it all makes sense. So yeah, so this is a very important feature of NumPy arrays, which I use a lot, in my research, and so it is very important to keep this in mind that one can do stuff like this. Again, also, one can do this exact same thing using for loops and if statements, but it just takes more time. And so that's why NumPy arrays have this functionality which speed your computational power, and so that's why using this in place of for loops or if statements is always better. In addition to this, one more feature that's crucial is one can sort of manipulate elements inside the array. So again, let's consider A, and if I want to reverse the elements inside A, all I have to do is just do a semicolon -1. So now I don't know the exact reason, why. I guess it's just the syntax, like the way we have to input it for it to be reversed. And so if you just type this, it's gonna reverse the array. So if you run that, it's gonna be instead of 1, 2, 3, 4, it's gonna be 9, 8, 7, 6, 5, so on. And so yeah, that's also an important feature. Another feature is is that I think I talked about this earlier as well, but one can obtain a subset by just selecting over which indices you want. So here, if I just want the first two elements, I just do 0, semicolon 2, and it chooses the elements which have an index value of 0 and 1 without 2. And so if I just do this 4, it's going to choose the values which have an index value of 0, 1, 2, 3. So fairly straightforward. I can also go beyond this and maybe maybe some more fancy tricks, like just skip every other element. So there, what I have to do is I just do again a double semicolon, but then sorry, I put a 2 here, and so that just means that it's going to skip every other element. And as you can see here, that it does skip for 2, 4, 5, 6. So 2, 4, 6, 2, 4, 6, 8. Yeah. And again, it's not just for just every other element, but I can also skip 2 elements at a time. And so I can just do that by putting 3 here. So the main point here is that NumPy arrays have a lot of super nice features using using their indexing features, using this a semicolon and stuff like that. And so just being aware of this stuff can be done is just very nice because they make life much easier. So okay, so that's all I'll talk about NumPy arrays. If there are any questions, feel free to ask. Otherwise, I'll go on to a very important topic called spline fitting, which is also one of my favorite topics, I would say. So if there, yeah, I'll wait for a few seconds. If not, I'll just move on. Okay. Okay, spline fitting. So now, when it comes to real life data, we never have perfect data. There's always going to be some issue, a systematic issue, some uncertainty, and that sort of makes our data sort of scattered across the actual relation. And so the thing is that scatter is not always real. The actual phenomena has no scatter, but it's just because our systematic uncertainties cause the scatter. And so if you want to sort of find a way to find the actual relation, or I guess predict the actual relation without accounting for these errors, what people initially do is they try to smooth over these errors. And one instance of this is called spline fitting. So basically in spline fitting, what we do is that you have a bunch of data points and you're trying to fit a smooth function that goes through these points. And these smooth functions that we fit are basically cubic polynomials. There's x cubed, x squared, those kind of expressions. And we have the ability to control the smoothness of a fit. So if I say, okay, fit these 10 data points. Now one can force it to go through every single point, which means that its smoothness is going to be 0. But if I say let's smooth this fit a bit, then what that's going to mean is that it's going to sort of not go through every single point, but sort of average over all the points. So I just like to make it more smooth, and that's basically what you can do in spline fitting. I think things will be more clear if I show an example. So I have an example here. Okay, so first, the spline fitting is part of this package called SciPy, which I'm sure you have heard earlier on Monday. And in SciPy, you go to the sub package called interpolate. So you from SciPy.interpolate, you import this function called as univariate spline. And this is the function which will be used to do spline fitting. And so now first let's make some fake data because we don't have actual stuff to work with now. So let's say X data, let's just make 100 equal points between 0 and pi. Again, remember the numpy.linspace function and what it does. And let's consider the sine function. Okay, so our y points are just going to be the sine of these x points, which these x points are just angles because it's between 0 and pi. And let's add some artificial scatter here. So now what this term is doing here is, so first of all, what does numpy.random.rand do? This makes, this is gonna give us a random number between 0 and 1. And what it takes in this function n is basically how many such random numbers between 0 and 1 we want. And as I have 100 points here, I want 100 values. And so that's why I put an n here. But the thing is, these give me values between 0 and 1. But say I want to scale that number to between not 0 and 1, but say -1 and 1, or like minus 0.1 and say between positive 0.1 and minus 0.1. And so that's why over here I scale those random numbers to the range between 0.1 and minus 0.1. And so now I have my x points and I have my y points with some like scatter. And so now what I'm going to do is I'm going to plot this data which I just made and the actual relation. So as you can see here, I first called the plt.figure. We have I don't think we talked about this a lot, but so I guess I'll just like talk about this more now. So when you make a figure, one has the power to like change the size of the figure. So here, when you call the plt.figure object or like this function, one can input in fixed size. And so what this fixed size does is it tells you like how many units wide and how many units tall. So this is like x. So the 6 is like the x units and 3 is the y units. And so if I want a figure to be wide and kind of like small in height, then I'll just make it 6 feet, for instance. So this is how one can change the size of figures. Now I want to plot my data as a scatter point. So that's why I'm going to do plt.scatter with my x data, which is defined above here, and y data. And also I have the power to change the size of these scatter points. So I put like 10 here because it kind of like looks reasonable, but it's up to you completely. And I can also like label my points because if you have like many points on the same plot, then it's hard to tell which is being plotted and what. And so having a label is always nice. And so this label is I'm going to call as a data points. This are actually, you know what, it's not native. It's sort of like a formatting thing. So I'll just avoid the confusion. So yeah, so I'm going to label it as data points. And now I'll plot the actual relation. This is x data and the corresponding function sine of x data. And I'm gonna change its color because I want it to look different than the blue points. And so I can force it to be a different color by just putting the color argument here and just mentioning as a string or passing as a string which specific color I want. So here I put dark orange, but there are like so many different colors. So if you search up like matplotlib colors, you will find the entire list of them. So feel free to look at that. And again, I want to label the actual relation. So I label that. Then to plot the legend, I'll have to call the plt.legend function. And so I call that over here. And then the font size, which like kind of tells me like how large I want my legend to be. And then I just plot this plot by doing plt.show. And if I run this, this gives me the plot which I showed earlier. And so yeah, and so we see that this blue data, which let's just assume that we sort of like measured that, like we measured these blue points through some experiment. We see the scatter here. Now, if I want to predict what the actual relation is, it's kind of hard to, like, I mean, like we can visually see what it looks like, but like how do we quantify this? And so that's where we talk about spline fitting. And so, okay, now let's do spline fitting. Okay, so now, as I said
Raj, we have a
earlier,
question.
oh, question?
Someone in the chat asked, how does it know what x underscore points is the variable, I assume? Did we define it somewhere?
Oh, I think I misspoke. It's x data, not x points. So, okay, so the first argument of the PLT scatter or PLT plot is going to be like the x points. So here I've defined x data, and so that's why if I put x data here, it's going to like plot that on the x-axis, those values, and then the second argument is going to be the y values, which I've already defined up here as y data. And so
I meant like in the np.sine function, like where you put an x.
Here. Oh, wait. Oh, okay. Here's a classic. Okay, I think this is a good moment to stop here. So, okay, Jupyter Notebooks has this really weird feature. Is that say when I start this notebook and I say let's call x point something equal to 4 for instance, and if I like say let's remove it because I don't need it. A Jupyter notebook still remembers it. And so what happened here is that when I was making this notebook, I labeled x data as actually x points there first, but then I changed it to x data. Then I forgot to change that here. And that's why it still remembers that I talked about x points earlier, but it still exists like in its kind of like memory. And so it's really, and yeah, so sometimes this like causes big issues and it's hard to like pinpoint, but like you had a very good eye and so you spotted the mistakes. That's very good. So if I just call this x data again, it's gonna like be again normal. So yeah, very, very good question. I'm glad you caught that.
Wait, so it doesn't delete it like thing in memory once you like run it again?
Okay. To be more precise, if you restart this entire notebook, so for instance, if you go here, if you restart the kernel, if you go here, kernel, and restart the entire kernel, then it's gonna like it's gonna forget all its previous assignments. But if you don't restart it and just like run it again and again, it's gonna retain its memory. So for instance, if I do like let's do xp is equal to 5, okay, and then let's remove this for instance, and then if I just do print xp, bingo, prints 5. But then if I restart the kernel, it says all variables will be lost. And if I restart this and I print this again, it says xp is not defined. So yeah, and so now I'll have to rerun all these cells because now all previous memory is lost, and so I'll have to run this again. But yeah, that's how. Yeah, so sometimes it's a good thing, sometimes it's a bad thing. I would say for me, it's usually a bad thing because you, yeah. But yeah, one has to be super careful about that. Yeah. Hopefully that answered your question.
Yeah. Thank you.
Yeah. Okay. So back to spline fitting. So I mentioned earlier that this function called is univariate spline that does the spline fitting. So what are its inputs? So its inputs are they are just the x points, the y points, and the smoothing factor. So this smoothing factor just tells you like how much smooth you want your function to be, or like your interpolated function to be. And if I force it to be 0, then it's gonna force that smoothed function to go through every single point. And so And so once I pass through this function, it's gonna return an object called spline smooth, as I've just labeled here. And this essentially acts as a function. And so if I pass in any x value to this, is this gonna like return the corresponding the y value for this like smoothed function? So I don't know if that makes sense, but I'll show an example. So if I run this, well, Okay, see X points again. I think I must, yeah, it should be X data here, yeah. X data here. Have I X points again? No. Yeah, no more. Okay, so here, so you can see, this blue points is our original data, and the orange is the actual relation, and the red is the spline which we fitted. So as you can see, it's not a very good fit, and so this is what it's called an overfit. Like we're fitting the trends in data too much. Like these trends aren't real; it's just scattered. And so here, it would be nice to smooth this data because there's some inherent noise in the system apparently. And so if I just say change my smoothing up to, I don't know, say 0.3 maybe. If I run this again, you can see it's much more smooth now, and it actually looks very close to the actual relation. And again, it's like one can just play with this, like the smoothing value. Like maybe 0.3 is too small. If I bump this up to 0.4, is it better? Oh, it's almost, yeah, it looks much better now actually. And this actually, like, so to fit this red line, you needed no prior knowledge of what this data actually is. All it did was that I gave it some X points, I just gave it some points and like a smoothing value, like how much I wanted to smooth the data. And then it fits this like line through all the data. And as you can see, in like, for instance, in this case, it actually fits the action relation quite well. And so like it's able to predict the underlying trend without giving importance to that scatter or noise. And so, as you can imagine, this will be a very useful tool in science because we always have like noise in science, and we wish to like predict find the underlying trends. And so, using this sort of spline is like one way to do it. And another use of splines is that, so as I mentioned earlier, so this spline object, it gives you like a function which like if you pass in an any x, it gives you a corresponding y. And so if you say have some data, which you like know is true, but it only exists at like a few points, then what you do is that you make the spline function by passing those points into univariate spline, and it's going to return a functional form that sort of fits the entire data you have. It also predicts data in between the points, and like that is also very useful, like in cases where you don't know like how the function it acts within points, but you like make an assumption that it's going to behave similarly to those other points. But a word of caution is that if you try to use the spline function to predict, say, beyond this range, so if I run this, it's probably going to fail like very badly. It does fail pretty bad. Like thing is, we used the sine function, but like as you can see, this is not a sine function at all. And so one point to keep in mind is that this is only interpolation and not extrapolation. So by word inter, it means it's going to only find values of the function within the points, like inter points. But then if you do extrapolation, it's going to predict the value of the function beyond the points you have, or beyond the range of the points you have. And for that, we use like other methods, which I think fall under like machine learning. But here, this is interpolation. So there's no extrapolation here, it's just interpolation. So that is an important point to keep in mind when using splines. So that was basically like all about splines. Are there any questions or comments about spline?
We have one question.
If you're trying to communicate right up your research in an article, how would you explain that this is what you did to your data? One would say like, that we have data here. I will add, like, if you want to answer, also answer, but I think personally for me, I would just say that like, so in a real science article, one would have to be more cautious, is that we only have finite data points. And when we do spline fitting, we're sort of like assuming that it's acting as if, so it's acting the same in the entire regime, which may not be the case always. And so when you like use this in science, one have to be careful. And I mentioned that like, here we're smoothing over the points, but we have like a reasonable idea that it should act like it should act in a smooth manner in that entire regime. And so using a spline approximation is a good approximation for data. I think
Yeah,
that's
so
what, yeah.
Can I
Well,
continue off that?
Yeah, sure, yeah, please.
Yeah, so I think Raj said a bunch of good things there. I think one thing to emphasize is why you would want to use the spline again. It's mainly for things that you know, or curves that you know are likely to be non-parametric. Or there's noise about some form of a curve that makes it hard to fit otherwise. So if you have a curve that doesn't fit some nice x squared or e to the x relationship, this can be one way to fit a curve and interpolate data points in the case where you can't write a mathematical equation down. And so in that case, you would say in your text, for example, we fit a first order or second order spline in order to approximate the data is probably the clearest statement of what you would say.
And also, these splines are basically cubic polynomials. So you could also say that if we're fitting, or like we're fitting a third degree function to data. Yeah, that's basically what you kind of do. Yeah. Hopefully that answered your question. Are there any other questions?
So is there ever like a point in using like low S values for a spline, or is it like just always generally beneficial to use the highest S values that you can?
So in at least my experience, okay, you know what, I'll show an example. So if I do say S100, insanely large smoothness, this is probably going to fail. Let's see what happens. Okay. Here it did not fail actually.
Your physical relationship is too good.
Yeah, that's
maybe
true.
Make your noise larger.
Yeah. so there are a few cases where, let's see, okay. You know what, if I do this, it's probably maybe better. 2 pi. If I do that 2 pi, let's see this. Let's do it. Let's see this pair. Okay, I think this might do the trick. Okay, so if I run this, and let's see how, now if I stick with my earlier smoothing value, so I think that's 0.4. So as you can see, it no longer that same value for smoothing is like no longer like valid, or not unvalid, but like it's not like, it's not giving us the same results. And so each problem is going to like involve some experimentation, like which smoothing value is sort of suits your question the best. And if I just make this very, very large, I don't know, I probably should, no, it's again, okay, so like I think this is not the best example, but there are cases where, like, for instance, if I just choose a very large smoothing value, is just going to show like no trend, like it's just going to be flat. I think if I increase the scatter more, it might be able to show this. Let's see. No, it's still showing. You know what? It's okay. But yeah. So if you choose a very, very large value, it's gonna underfit the trend. I think it's gonna underfit. So like trends which it thinks, so it's trends which actually exist, this might think that that's just noise, and so it's going to not fit that. And so having a very large smoothing value is also not good, but having very low, as you saw, like if I just do 0 here, it's going to be like complete like just noise. It's like, this makes no sense. And so it's all about like finding the balance between like overfitting and overfitting and underfitting. So personally here, if I can experiment. So 1, if I do 4, that's still very noisy. If I go to maybe 40, it's okay. Things are looking slightly better. But yeah, so it's basically about like experimentation. So yeah, here it seems to be doing a pretty decent job. So yeah, hopefully that answered your question.
And if I can add something. So one criticism of splines, hate to do this to you, Raj, is that you're sort of seeing,
it's very important, yeah.
You're seeing what live why you might not want to use them when you know that there's supposed to be an underlying physical relationship, right? Because if you looked at the two curves on screen, it could be hard to quantify which one of those is better. there are mathematical ways you can try to do that, but in general, if you know that you're expecting a sign, it's much better to try to curve fit to a sign. And Viraj is using this very noisy example where you could see why this spline might be useful, but I think the word of caution is if you can use something that's parametric where you know the functional form and you can, find the coefficients of that functional form that minimize the scatter, that's probably a better option, but that's not always possible.
Yeah, absolutely right. Yeah. Are there any more questions? Okay, if not, okay. So this latter part was just like kind of like an additional example, which we don't have to like walk through right now. Like it's something which you can read on your own because I wrote like a lot of text, as you can see. It's quite sort of like self-explanatory. So if there's time, I can go there. But I would first like to just ask a question, like if there's any previous topic in the workshop which you have some sort of issue with, or something which you would want us to explain again. Now is the time where we can do it. So if there are any any sort of lingering questions or anything, feel free to ask. I'll wait for a few moments. If not, I'll just sort of skim this entire part because this is like pretty large, so it's impossible within like 20 minutes for sure. But yeah, I will be sending this over afterwards, so don't worry about that. But yeah, any questions about previous topics or anything? Or any questions that like arise out of this spline thing? Yeah, because like this spline thing is kind of crucial, and it does open up a lot of fields in like sort of coding. Like, how does one fit data then? Like, how does one fit a functional form? And that's when things start getting like more computationally intensive and like more complicated. And I think so. Yeah. So like for the scope of this workshop, going into there is not the best idea, I think. And I think Will actually mention a few methods. I think you talked about regression or no? I forget if you did.
Yeah, so I talked about basic linear regression.
Yeah. So I think like for the scope of this current workshop, like now, that's sort of like enough. But there's like loads of other stuff. Like for instance, if you're curious, you can look up MCMC, which is sort of like the basic idea is that you have some data and you have like a predicted functional form. Let's say f is the function, and I say 3 variables ABC. So like f is a function of 3 variables ABC, and you're trying to fit this functional form to this data, and this data takes like some values of ABC which we don't know. And so how does one find these values of ABC? And so that's basically what happens in MCMC, where it sort of like explores the entire space of like all possible values of A, all possible values of B and C, and then it sort of like finds the values at which it's the best fit. So I think like this is like by far the most popular method in science that's used to like fit predicted functional forms to data. And as of now, I think it might be a bit overkill to like talk about that in this specific workshop, because it is like a bit complicated and like it needs some like knowledge of coding. But we hope that maybe like after this workshop, maybe next quarter or something, or like maybe like even this quarter, we might like write up like a small notebook that explains this stuff in more depth. And so, yeah, so just just saying that if you're interested, that's something. But yeah, okay. It seems like people don't have any questions, so that's okay. No worries. I guess I'll just like sort of steamroll through this thing. So okay, so basically this is an example where we'll use like your previous knowledge of coding, like we should learn like for loops, if statements, how to load a text file and stuff like that, and to like use all that knowledge to analyze a dark matter simulation. So for people who don't know what a dark matter is, just like a one sentence thing is that, okay, so matter isn't just a matter that we see around us isn't just made up of like, you know, protons and neutrons. Scientists have found that there's this new kind of matter. It's called this invisible matter, or it's called this dark matter, that fills our universe, and it's 5 times more common than like this like normal matter we see around us. And we still don't know like what makes, like what is the composition of this new kind of matter and stuff like that. So it's still like an active area of investigation, but we know a lot about it based on like just doing indirect observations, like enough space, and also like doing massive simulation. So here we'll be looking at data from a dark matter simulation. Again, if you want some more information, it's all over here. I won't go into like depth while I'm speaking, but yeah, just to see like, you know, how like a dark matter simulation looks. Here are a few awesome photos which I like to show. And these photos, they are from a specific simulation called the Millennium simulation, which was run by the Max Planck Institute, I believe. And yeah, and so like I think this is the largest simulation we have run till now, or maybe there's another one, but yeah, I forget. But yeah, this is like a very, very large simulation. It's like much larger than like a single galaxy. So it's like massive scales, and like it has helped science a lot for sure, but also it gives us nice plot like this, and so it's always nice to appreciate the artistic side of science. But yeah, here's all the information about this stuff like that. So just, you know, once I send this, you can read some more depth. But yeah, I'll move on. So here in this notebook, I'll be looking at a specific a simulation called as ELVIS. ELVIS simulation, which actually stands for, it's not just, you know, named after the singer Elvis Presley, but it also has its own acronym, just I would say a very smart acronym. It's called Exploring the Local Volume in Simulations. And the local volume is just like the volume around our Milky Way galaxy. So it's like just the local area. So yeah, anyways, so when one looks at the data, what's the first step? So first we want to import the packages that we'll be using. So I've already imported NumPy, which is like going to be your main package. Also, Will talked about pandas, but thing is, sometimes data is organized in a very poor way, like it's done here in ELVIS, I would say, and you cannot use pandas. And so that's why you use another way called numpy.load text file. And so I'll briefly mention that here. So, okay, anyways, yeah, so you'll have to read this file first, and then, okay, again, it's like a bunch of stuff here, but for now, just, you know, ignore this part. Okay, so now about loading the data. So we talked about strings earlier. Now, but we haven't like talked about, like, I guess, the usefulness of like where strings are used or are the most useful. And they're very useful in loading files, as you can imagine, because the name of a file is basically like a string object. So if I have a text file called, say, ibird.txt, I cannot like load it like this. Like I'm gonna like load it as a string. And so that's why strings are very useful here. And so first thing you'll have to know is that the path, like, because the thing is, this Jupyter notebook does not know where this file is inside your laptop. If it's in the same folder as this notebook, then it probably will tell, like, you know, okay, I know where it is. But if it's somewhere else, then it has no way to tell where this folder is. And so that's why one can specify a path. So here, as you can see, this is the path to my file. So if I just load this, and if I just print my data, my path scale, just go to path scale, as you can see, this is a complete path to my text file. And so, and at the end, I wish to load this text file. And the way in one can actually, and so one way in which one can load such files, like this text files, is using the NumPy function called load txt. So it takes in like, its argument is the file, or like the path to the file. And so if I run this, then it's going to store all the data inside the text file in this variable called as path scale. And if I just print this, it's just like oh no, my bad. It's in data scale, not path scale. It's in data scale. And if I roll this, it's just like a bunch of data. And now it's hard to tell like what this actually means. And so that's why it's useful to print the shape of the data, like what is the like format. So so NumPy shape gives me like the shape of this, like what is the shape of the data. And what this tells you is it's basically a matrix with rows and columns. So it has 1278 rows and 75 columns. Now, when we talk about a dark matter assimilation, what is actually happening is that in the assimilation, you have a bunch of particles, like you have a bunch of dark matter particles, and these particles, they move in space, they evolve in time, they increase their mass, they lose mass, and stuff like that. And so when one says I'm looking at a dark matter simulation, that's basically what one is doing. One is looking at how these individual particles of dark matter or objects evolve in time. And so here, so I know like how the text file looks, and so that's why I can tell is that we have this text file stores 1,278 rows, which correspond to each single dark matter object, and there are 75 columns, which are like basically your 75 different values for each row. And what the scale thing here is, so in astrophysics, a scale factor, which is like actually a very important thing. I've explained it, like I've explained it in more depth above, but for now, it's just like it's just a time unit. So like as one as seconds and in years, scale factor is also like a time unit. Yeah. And so what this is telling me is that it's giving me the information at like which times I'm extracting the information of the halo for each individual halo. Like no wait, I said, oh my bad, just object. Okay, so what this is telling me is that for each row, which is a single halo, it's giving me the times at which I'm looking at the object. And so in the entire simulation, so once I start running the simulation till the end, I look at the object, or like I look at the status of the object at 75 different times. And the times at which I look at them is basically encoded here. And so for each object, yeah, so that's basically what this is like, saying here. And all this information is like loaded in this text file. And so that's one part of it. Now, we know the times at which we're looking at these objects. Now, when we look at these objects inside the simulation, we don't like just look for fun. We want to store the properties at those specific times. Like what is the mass that what is the mass of the object? So okay, I'm saying object a lot, but a better term is a halo. So it's called as a dark matter halo. So a halo is basically like a big blob of dark matter. It's like that's like what it's called. So I'll call a dark matter object as a halo from now on. Again, all these terms are explained properly in this notebook, but for now I'm sort of like just talking about how one approaches like looking at a data set. And so yeah, and so if I look at say the first row of this data scale, and if I just print it, so again this is all goes back to what we've been learning, that we have an array and unprint the first element. So over here, what is interesting is that the first element is not a single number, it's like actually an array. And so it's basically like a matrix, like a matrix, like one row is like an entire vector, or like one row is like an entire list of numbers and not just a single number. While a vector, one row is just a single number. And so that's basically like the thing here, is that a data scale is a 2D matrix. And we have in the past only talking about 1D arrays, or like 1D matrices. And so the first element in this 2D matrix is going to be it's going to be a list, or like, or to be more specific, a NumPy array. And so if I just print the first row of this matrix by just calling the first index 0, it prints out all the time. So again, these are scale factors, and this is again like a time unit, but I won't talk about much about now, but it's all explained. It's all explained here, like what it means. But yeah, and so these are like sort of the 75 different times. So 0 is like the start of the simulation, and 1 is like the end. And so, yeah, and so these are the times at which we like look at these objects. Okay, that's one thing. Now we talked about filtering. So the thing is, 0 is a bad number to work with, and it's best if we like it's best if we just like remove this 0. And so, as I mentioned earlier, is that we can always like filter NumPy arrays. And so, let's say I choose the first row, and I label it as this, and then I'm going to filter this. Where again, if you recall, it's just simple that you just call the NumPy array, and then inside it you input the condition with which you want to filter. And if you see, if you return it, all those zeros are gone. So awesome, we are able to filter stuff. Okay, that's something. So here again, something that's not important, but it's just that if you want to go from like say scale factor, which is this time unit here, to like time in years, that's what you do. So this is sort of like this isn't like sort of like part of like if you like know the code, it's just that these AstroPy. So AstroPy is just like a package in like Python that is like very popular, and it's used a lot in like astrophysics, and it has like a lot of useful functions like like for instance like being like transforming between years to scale factor. So this is like the standard way to do that. And so I just copied this from like the AstroPy docs that like just how to convert scale factors to years and vice versa. So this is just from the docs, but yeah. And so as you can see here, if I just input in the scale factor of 1, which I said earlier, 1 means the present time, and if I print the value, oh my bad, it's going to give me the time of the current universe in years, which is actually 13 point, roughly, this in years. So just, it makes sense, yeah. And anyways, yeah, okay. What else should I talk about? Yeah, okay, also, okay, so up here we loaded a text file called a scale.txt, but there are like other files in the data. I'll also be sharing the data, so you can just like explore all this stuff on your own. I'm just like sort of like walking through the first steps, so that then it isn't completely new when you try this on your own. And yeah, so MVir, again, it's an astrophysics term which I've explained about, but for now just like take it as a mass. It's the mass of the object. And so this text file, what it stores is at each of those time steps when I look at the halo or the dark matter object, what is the mass? And if again, like, it's again, like I first find the path. So if this path MVir, it's the path to that file. And then I just use numpy.load.txt to load the file. And then again, it has the same shape as the one we saw above, which has time, which makes sense because you're looking at those times and then you're finding the mass at those times. And so if there has to be like a one-to-one correspondence between the times at which you observe and the mass at the same time. And so that's why it makes sense that they have the same shape. And again, if I load the first row of this 2D matrix, which just corresponds to the mass of the first halo, I can see that these give me masses, and so these are pretty big masses. You can see like they're like 10 to the power 12, and these are in units of solar masses. So these are pretty massive. Like that's a lot of suns. And yeah, so one sort of like has information about how the mass of an object evolves in time now, and so just very useful stuff. And again, so these zeros which you see here, these are basically the times when this object wasn't defined. And yeah, so like inside a simulation, like we have a bunch of small particles, and then these small particles, they kind of like combine to form a bigger particle, which then if that particle is large enough to be observed, but not observed, to be like sensed by the simulation, then it starts recording its value. So at these two times, it wasn't that big enough, and so that's why there's 0. And so we don't want times when the halo wasn't defined. And so again, we can filter them by doing what we did earlier, is that filter by 0 and stuff like that. So okay, we briefly talked about this. Now, okay, so now we sort of like just explore the data. So a big part of like, when you do research is that you get like a huge set of data. And your first task, and your first task is always going to be like looking at it, like how is this data formatted? What is data about? What are the columns, rows? Like how can I read? So having that down and just like properly knowing like what this data actually is very crucial. And so this so like this process which I walked you through is probably like what I would do when I look at like a data for the first time. It's like printing different values, like just seeing physically what is in the data. So that's also a very important part of research. And yeah, okay. And so here is where I write a function actually to do all this above steps. So here again, functions are very useful because if you sense that you're doing something, or if you sense that you're doing a task again and again, that probably means that you're being inefficient and you need to write a function for it. Because functions, that's what their purpose is that if you have some procedure which you want to do, and it's something which you will like do again and again, it's best to like write a function, because then next time when you want to go through that process, one does not have to copy the code again and just like run it all over again. One has to just write a function, and then one just calls the function by like a simple one line of code. And so here's where I write a function that sort of does all this stuff. So I'll just walk you guys through this function, and then I'll stop. Then I think this, and then I think the rest is fairly self-explanatory. So okay, so I have a function which I'm going to define it as read a simulation. Again, as a reminder, a function, it starts with def, and then you have the name of the function, and then you pass the arguments which you want to pass into the function, and then you have a semicolon, and then you indent by a tab space, as you can see here, and then you write the entire function like this. And it's usually also good practice to like comment your function. So in coding, always, when you're coding, it might seem like, why I have to comment. Like for instance, if I do here, then read this text file. Like for me, I know what I'm doing, so it's sort of like, why. But then if you want to share this code to a friend of yours, or if you're going to come back to this code, let's say after a few months, then it might be very hard to like keep track of what is actually happening. And so it's always good practice to comment your code. And so yeah, like as you can see, I comment pretty excessively. So that's why it's like easier for me to follow like what I'm actually doing. And also, one can comment for functions like this, like so you have like three apostrophes here, and so then 3 apostrophes below here, and then this part in the middle is basically all the comments. And so one can also give like more information about what this function is doing in like, in just plain English. And so as you can see, input, I just input in the name of the object. So it's just like which simulation I want to read, and input format is a string, and output is just going to be a NumPy array of filtered times and masses. And so if I just read this, I like now know within like a second like what this function does. But if it wasn't for this, I'd probably have to like read this code and see what's happening, which would for sure take like more time. And so okay, so I input in the halo name, which is a string, and then based on this name, I define my paths, because the way these paths are defined in this relation is based on like the name of the halos. And so I define all the paths. As you can see here, I want to read these two files, mvir.txt and scale.txt. And so I have these two paths for them, halo.mvir and halo.scale. And then I load the text files as we did. So this is basically all the process we did earlier, but now it's like condensed in a function form, which is easier to use. And so we then load the text file. So we load the mass data and we load the scale data. And then I define two empty lists. So again, if you remember, the way we like sort of like, do is that if you want to input something that isn't sort of like defined, then we can like first define it as empty list, and then we can like add stuff to it. And so that's what I'm, sorry, that's what is happening here, is that I'm going to first define an empty list, and then I'm going to add stuff to this as I make them. And so for loop, so what I do is that, okay, so I mentioned earlier, like, the shape is, so it has 1278 rows. And so if I just if I just print the length of this data, it's going to just give me the number of rows in this data. It's going to give me, oh, not L-E-N, L-E-N. And so it's going to give me, wait, data. Oh, I didn't load this, my bad. Okay, so it gives me 12 seconds. So it says that each element in this data set is like a single row, a single object. And so in a for loop, I'm ranging, so I'm looping over all these individual objects. And if you also remember, I think last week I talked about multiple ways to like loop over. So range len is one way. There's also enumerate. So yeah, so if you don't remember, refer back to that notebook, but yeah. And so I loop through each object in this data set. Then what it does here is so I is the index, but I don't want the index. I want like the actual row. And so I return the rows by just like calling the ith index of that entire set. And then I filter it as we did above. And then I convert the scale factor to time, which I also showed about, which was like, so it's all like, so this entire function sort of like condenses that entire process in a few lines of code. And so now I have my filtered masses, which are called MVIF, and I have my filtered times in years, which are TI, and then these are the things which I want. And so then as I want these things, I'll append these. So these are again lists, and I append these objects to these empty lists. And so as I loop over each time, as I loop over each object in this entire data set, it's gonna add these things to this. And at the end, once it finishes, it's gonna then finish this. So yeah, so once this loop is finished, it then goes to the next line, and then it's gonna like return those lists. So then it converts those listing arrays. And why we do that is just because, as we saw, as we saw many times, that we want to work with arrays more than lists, because lists are sort of like not that useful. And so we convert them to arrays, and then I just return those two as, as the function's output. And so if I define this function, correct, and now here's a sample run. So I'm gonna run this on like this Halo set called as iChair. And if I run this, it's gonna return two outputs. So that's why I have like these two things here. So iChair times and iChair MVs, masses basically, and equal to the output. So this has two outputs, and that's why I need two things here. And once I run this, it's gonna go through this entire thing. So yeah, that's basically a function. Now, one last thing is that, one last thing. As you can see, that there's this bar here that's like moving. This is a very useful part of Python. It's in this package called as TQDM. It tells you how far the loop is in the entire like looping process. So say you're looping over 1,000 items, but if I just do like for I in range 1,000, if I just print print I. If I run this, it's hard to tell like where we are right now, like which part of the loop we are right now. And so that's why having a progress bar that tells you like how far you are in the loop is very useful. And it's also especially useful when your for loop takes a long time, as it does here. Like it's not fast, but also like not super long. So here it's like fine. But in like most cases, it might take like 5 minutes, 10 minutes, maybe like 1 hour to run the entire loop. And so just having an idea like how far you are in the progress is very useful. And so like if you just wrap your for loop around this function TQDM, it just tells you like how far you're in. So yeah, that's just like the fun feature of Python. But yeah, that's all about it now. There's a bunch of stuff here that's very fun stuff that I talk about here, but all this stuff I think I've explained very properly. So I will share this notebook with you guys in a few, I guess, like after this class, and then you can just like go through this on your own and just explore stuff. So yeah, that is it for this workshop. Hopefully I didn't confuse you guys too much with what I like talk about here. But yeah, okay. I'll stop sharing. Or if you have any questions, feel free to ask now. If not, I'll stop sharing. And yeah, thank you all for attending. Also, as a reminder, an email was sent out in the morning about which projects you might want to work in. So thing is, yeah, so like now we have basically sort of like finished the teaching portion, like the explicit teaching portion. The project also is going to involve teaching for sure, like because like when one does a project, it's basically like you're learning how to like use coding in this context. And so, but yeah, from next week we won't have any like weekly classes like this. It's just going to be like you'll be connected with your leaders with the project, and then you'll just like talk amongst yourselves like about project stuff like that, like when you'll meet and stuff like that. And yeah, so that's about the project. And so the project again, like it probably will like last for a few weeks. It won't be too time intensive because we like because like we have classes and stuff, and so it's hard to balance always like a big project and like a class. And so the project is hopefully not too time intensive. And then at the end, it's just going to involve like you write like a report of like what you learned in the project, what you did, and some final results. And then if you finish that, and then if you like write that report successfully, then you will like get a piece of paper that says XYZ student did this and has successfully finished this workshop, which will be pretty cool. And yeah, and I will send like an email out that I sort of like just recaps like all the stuff that I said about projects. And yeah, that's it. Yeah. Are there any questions about the project or anything that I missed? If not, you can always, like always email me. So I guess, yeah, I guess there aren't any questions. So I guess we can call it a day here. So, okay. Have a good day or good night, everybody. Hopefully your midterms aren't too intensive on you guys. So yeah, see you guys. Bye-bye.
All right, thank you.
Thank you.